In this session, we'll be looking at block cipher modes. So we have learned what is a block cipher in the last session. So what is a block cipher? You take a message, you take any message, and then what you're going to do is you're going to divide that into blocks. So we're going to divide that into blocks of fixed size. So each block can be of 64 bits or 128 or 256. It depends. So we will divide a message into fixed size blocks. And what we'll do is we'll use a encryption strategy to actually encrypt each block to ciphertext. So let's consider blocks to be P1, P2, P3, P4, and we will use an encryption strategy with a key that converts that to a ciphertext C1, C2, C3, and C4. This is what we have understood with respect to block cipher. Now we are going to look at the various modes of block cipher operation. Why we need different modes? That is the first question. Say I have so many blocks here. I can either encrypt all of them in parallel. I can do that, right? I can take all the blocks and encrypt them in parallel. Well, that becomes one of the modes. The next mode can be the importance can be given to the security of the encryption. So I can just chain the blocks and encode. So that is another mode. So what kind of strategy we're going to use depends on the kind of message that we're going to pass. So block cipher offers us many modes, and today we'll be looking at all the modes. So these are the modes. We have electronic codebook mode, that is the first mode, and next cipher block chaining mode, and counter mode, cipher feedback mode, and output feedback mode. We'll be looking at all these modes and the advantages and disadvantages of opting for these modes. Let us start with the very first mode, electronic codebook. And before starting off this mode, we have to understand certain things. Say, let us consider that our message is divided into many blocks. And this message is nothing but plain text. And we call each block of plain text as P1, P2, P3, P4. We can consider each block to be 64 bits in length. So that's our idea. And what we do here in electronic codebook mode is we take each block of plain text, we feed it to our encryption algorithm, and this algorithm uses a key and we get the output as a ciphertext C1. So again, this is block 2 from a message. It is being fed to the encryption algorithm, the key, and then we get cipher 2. So every block is being fed parallelly to the encryption algorithm, and we are able to generate ciphertext parallelly. So this is called electronic code book mode. Let's look at decryption. So decryption in the sense we'll be having blocks of ciphertext. Say in block cipher, when you when you encrypt a block of plain text, we get blocks of ciphertext. So this is the encrypted blocks of ciphertext. And what we will do is in decryption, we'll be using the ciphertext and we'll be feeding it to our decryption algorithm. And it uses the key as usual, and the output is a plain text or the original message. So what we do for decryption, we take every block that has been encrypted, we parallelly feed it to our decryption algorithms, and what happens is it generates all the plain text. So again, decryption can happen in parallel. So what are the advantages of ECB mode? Parallel encryption of blocks, and so we attain faster encryption. Always keep this in mind. So what is the important advantage here? We have blocks. Each and every block is parallelly fed to our is parallelly fed to our encryption algorithms, and parallelly we can generate all the ciphertexts. So we attain faster encryption here. That is one of the important advantages. Let us look at the disadvantages here. So when you talk about disadvantages, say you consider all these things to be the plain text messages, plain text 1, plain text 2, plain text 3. If the messages repeat, for instance, if there is a message Satish CJ and there is another message that is repeating Satish CJ, this is block 1 and this is block 2. When we feed it to our encryption algorithm, we get ciphertext. Again, when we feed this block to the encryption algorithm, we get the ciphertext. Now, the point is when we have the messages to be the same, the ciphertext will also be the same. So this is one of the major disadvantages of ECB mode because a cryptanalyst or a hacker can very well understand the patterns in your text by looking at the ciphertext. Say for instance, an AND can repeat frequently in your messages. So there can be a ciphertext that is repeatedly generated like C1, C2 and C3 that actually matches. All the ciphertext will be the same for the input that is given. So if your input plain text is the same, then the output ciphertext will also be the same. This is one of the major problem with electronic codebook mode. That's why we don't use electronic codebook mode for lengthy messages. Maybe you just have one block of message and you want to send it, then ECB is preferred. But if you have repetitive blocks of messages and it's a lengthy message, definitely it's not good to opt for electronic codebook. So what is the application of ECB? Secure transmission of single values. We will not use it for lengthy messages. I hope you have understood what is electronic codebook mode in block ciphers. Let us take a look at the cipher blockchaining mode. So we understood in electronic codebook mode, when the plain text repeats, you're going to have the same ciphertext. So that becomes a weakness of the algorithm. And cipher block chaining mode is a more secure algorithm. So we'll see what it does. Let's consider that our plain text message is broken down into blocks. So we have three blocks here. This is P1 and P2 and P3. We can assume that each block is of 64 bits. What we are going to do here in cipher block chaining is take this first block and we are going to take an initialization vector. Say if our P1 is 64 bits, this initialization vector is a number. You can think that to be a random number that is of 64 bits, and this is an initialization vector. We can consider an initialization vector to be any number, any random number. And what we are going to do here is we are going to use this IV and we are going to perform an XOR operation with our 64 bits of plain text. So IV is 64 bits and P1 is 64 bits. We will do a bitwise XOR and this result will be feeding it to the encryption algorithm. And whatever ciphertext that's coming out will be used in our encryption of the next block. So let's take a look at the encryption of block number P2. So this block will be taken and the ciphertext 1 which we achieved by encrypting plain text block P1 will be fed as an input here and there will be an XOR between ciphertext of this phase with the plain text block 2 and obviously this will be 64 bits because our input is 64 bits. Here we have a plain text of 64 bits and this ciphertext of 64 bits will perform an XOR, will feed it to our encryption algorithm. Obviously we use a key and we get ciphertext 2. So we are chaining the results of the first block with the second block. So that's why it's called cipher block chaining mode. To understand it far better, we'll take P3. So this is plain text block P3 and what we are going to do here is we are going to take this ciphertext which we have received in this phase. We'll take this one. So this ciphertext is how many bits? 64 bits and this plain text is how many bits? 64 bits. And what we are going to do is we are going to perform a bitwise XOR operation. And this output of 64 bits will be going into an encryption algorithm, and we'll get ciphertext 3. And this will be further chained to the other blocks. So we have a chaining of blocks here in cipher block chaining mode. What is the advantage that we achieve? Say if the plaintext block contains a message Satish CJ, and plaintext 2 contains a message Satish CJ. Say plaintext 1 and plaintext 2 blocks are the same, they hold the same message, but when you go and encrypt that, here we are using an initialization vector to create randomness. So the output ciphertext 1 will not be equal to ciphertext 2. And we are also using the output of ciphertext 1 in encrypting the plaintext block 2. So definitely, even when the input plaintext blocks are the same, the output ciphertext will be different because of the randomization of the inputs. Now let us take a look at a small visualization of this. Say we have two plain text blocks. This is P1, P2. You can see here this is 64 bits and this is also 64 bits. And we have an initialization vector. I told you this is another number. This is used initially. So you call that IV. This is also 64 bits. So we take this block and we take the initialization vector. We perform an XOR. That is the first step. And then we feed this output to a encryption algorithm. So we feed 64 bits of this output to an encryption algorithm. This uses a key, and then this creates a ciphertext of 64 bits. We can call this ciphertext to be C1. So our encryption of block 1 P1 is done. Next we'll take plain text block P2, and this is plain text block P2. And what we are going to do is we are going to take this ciphertext here, and we're going to take the ciphertext C1 and we'll do an XOR with P2. This result of 64 bits will be sent to our encryption algorithm, and with this key we'll encrypt it to ciphertext C2. So like this ciphertext will be chained to further blocks. So one of the main advantages we achieve here is even when the plain text blocks hold the same message, the ciphertext are going to be different. That is about encryption in cipher block chaining. We look at decryption in cipher block chaining. So for decryption, we'll be working with ciphertext. So let's say we received all the ciphertext blocks C1, C2, and C3. What we are going to do here is we're going to take the first ciphertext block C1, give it to our decryption algorithm, and we'll use the key, we'll decrypt it, say we get 64 bits, and then we'll take the initialization vector that we used in our encryption phase, and then we'll do an XOR with this output so that we get our plain text block 1. And this ciphertext block 1 is also used in decrypting the further ciphertext blocks. So we take ciphertext block 2, we feed it to the decryption algorithm. Then what we do is we take the ciphertext block 1 and we do an XOR with this output of 64 bits so that we get plain text block 2. So again there is a chaining here with respect to decryption. You might have noticed that we are using this initialization vector in both encryption and decryption. So this initialization vector should be shared between both the participants in the communication. And this initialization vector should not be made public, and it should be shared in a very secure fashion. So what are the characteristics of CBC? We've already seen that the same plain text block, if repeated, produces different ciphertext blocks. So it overcomes the weakness in electronic codebook mode. Another thing is the initialization vector, which is used in the encryption phase, is also used in the decryption phase. So the sender and the receiver both should be having the initialization vector, but that should be unpredictable by a third party. So again, for maximum security, how to transfer this initialization vector? You see, initialization vector is just one block of 64 bits, right? So IV is just one block of 64 bits. We can very well use strategies like ECB, electronic codebook, to transfer the 64 bits to the user. What are the disadvantages of CBC? Parallel encryption is not possible. Say, if you have plain text of P1, we encrypt that using a strategy to C1, right? Whereas we cannot go and encrypt P2 unless we get C1, because we are going to use the C1, perform an XOR, and feed it to the encryption strategy. So what is the problem here is we cannot go ahead and encrypt P2 unless we have finished encrypting P1. So there is a wait on encryption here. So that is the disadvantage of CBC. Now we'll go to the third method, counter mode. Again, the advantage of counter mode is it permits parallel encryption and decryption. We'll see what this counter mode is. This counter mode uses a counter. You can also think that to be an initialization vector. And there is one small difference with the counter when you talk about an initialization vector. So this initialization vector is getting incremented. You see here, every time for every block, this counter gets incremented. They also say the counter to be a nonce or number used only once. Say you use 64 bits of some number. The only thing you have to keep in mind is for every other block that you're going to encrypt, this counter will be incremented. So we're going to use the counter data and we are going to send it to our encryption algorithm, encrypt it using a key. The output of 64 bits will then be XORed with the plain text to get the ciphertext block C1. Likewise, here we take the previous counter, increment it by 1, we feed it to an encryption strategy. You encrypt that, you get 64 bits, and you take 64 bits of plain text, you can XOR it, and then you get C2. So here, this counter gets incremented for every block. And you can see all the encryption can happen in parallel here. Again, what is the advantage here? Since we are using different counter values for each block of encryption, the ciphertext that we are going to achieve will be different even when the plain text message is going to be the same. So here we achieve parallel encryption and also we have overcome the weakness of electronic codebook mode because we are using different counter values for encrypting different blocks of plain text. So this is the counter mode. A counter equal to the plain text block size is used. If your plain text block size is 64 bits, counter is also 64 bits. The only requirement is the counter should be incremented for every block, or else the counter value must be different. Typically, the counter is initialized to some value and then incremented by 1 for each. For encryption, the counter is encrypted and they XORed with the plain text block to produce ciphertext block. See, there is no chaining here, hence parallel encryption and decryption is possible. So what we do for decryption, so as I told you, for decryption, we'll be working with only the ciphertext blocks. So let's say C1, C2, C3 are the ciphertext blocks. We'll take the counter. So this is the counter we have used for encryption too. And this will be incremented for every block of ciphertext we are going to decrypt. So here what we are doing is we don't have a different decryption algorithm. We are just going to use the counter. We are going to again encrypt it using the encryption algorithm itself. And it uses a key. Say we get 64 bits of output. Now to decrypt, what we are doing is we are just doing an XOR with the ciphertext. So an XOR with the ciphertext leads to the plain text. Likewise, let's talk about decrypting ciphertext block 2. So here we are incrementing the counter value, feeding it to the encryption algorithm, and we are getting 64 bits of output. What we are doing here is we are taking this output, we are doing an XOR with the ciphertext 2 to get the plain text 2. So that's how decryption happens in counter mode. What are the advantages of counter mode? I've already told you. You can you can take every block and you can encrypt it or decrypt it parallelly. So that is the main advantage. We can effectively use the hardware. In chaining modes, the algorithm must complete the computation on one block before beginning the next block. But here we can achieve parallel encryption and decryption. And even processes that support parallelism can be effectively used with counter mode. Pre-processing. This is another interesting thing. Say here, um, let's take a look at this. What we are doing here is, even before we get the plain text, we can actually keep this part ready, right? So we can have some counter value, we can encrypt it, and we can have the output ready. So we can have the output ready even before we get the plain text, and that is pre-processing. As and when we get the plain text, we'll perform an XOR and create the ciphertext. So even before we get the plain text, we can go ahead and keep our encryption uh, output ready. So that's also speeds up the process of encryption here. I hope you all have understood what is the counter mode. Okay, now let us understand the next block cipher mode, the cipher feedback mode. So what is the use of this mode? We can convert a block cipher into a stream cipher by using this mode. Let us consider a stream of bits, say stream of 8 bits coming in, say plain text P1 is 8 bits, P2 is again 8 bits. So we have a stream of 8 bits coming in. Actually, we need a stream cipher to encrypt this. We'll see how to use a block cipher and encrypt a stream of bits that is coming in. So the process starts like this. Say we'll have an initialization vector. This vector can be any number. Say it is of 64 bits in length. We feed that to our encryption algorithm with a key, and then we encrypt it. We get 64 bits as the output. So in this 64 bits, let's say we take the first S bits, that is say S is equal to 8. So we take the first 8 bits and we discard the remaining 56 bits. That is not needed. Why we take the first 8 bits is because our plain text will be coming in 8-bit streams. So what we do is we take the 8 bits from the encryption output, and then we take the 8 bits that stream of plain text that is coming in. We perform an XOR, we get our ciphertext. So what will be the ciphertext? It will be also 8 bits. So that is the very first step. And this ciphertext is given as an input to the next phase. So what is the next phase? We'll again take this initialization vector. This initialization vector is nothing but 64 bits in length. Let's say it's 64 bits. And we will left shift by S bits. What is S here? Say we assumed S to be 8. So when you do a left shift of this IV by 8 bits, what happens is we'll have 56 bits here, and then we'll have 8 bits remaining on this side. And what we are going to do for these 8 bits is we are going to take the ciphertext C1, which is 8 bits. We're going to put C1 here. So this will be 8 bits. So the total length will again be 64 bits. To understand it better, let me take a small example. Say if your initialization vector, say if it is 8 bits like this. So 1, 2, 3, 4, 5, 6, 7, 8. And when we do a left shift of 4 bits, what will happen? These 4 bits will be discarded. So we're going to have 1, 1, 1, 0. This will be the initialization vector after shifting it by 4 bits, that is left shifting by 4 bits. If our C1, if the C1 is 4 bits, if the ciphertext is 4 bits, what we'll do is we'll fit the ciphertext here. So C1 will be here. Let's assume the ciphertext to be some 1, 1, 1, 1. If this is a ciphertext C1, so since we have shifted 4 bits, we can very well fit the ciphertext here. So that is what is happening in this shift register. So we are left shifting the initialization vector by S bits. Here S is 8. And then we are taking this C1, which is 8 bits, and we are fitting it here. So we again get a 64 bits initialization vector, and this IV is not the same as this IV. We have some randomness to it, and now we feed it to the encryption strategy. We get the output. The output will also be 64 bits. In this, we'll take the leading 8 bits. Since we have assumed S to be 8, we'll take the leading 8 bits, discard the remaining 56 bits. We don't need that. And these 8 bits will be taken, and the plain text stream of 8 bits will be taken, and then an XOR is performed that will lead to C2. So C2 again will be 8 bits. So this process is repeated. So if you think of the next phase, again we'll have the shift register. Here we'll have the initialization vector now that can be taken from this phase, and it can be left shifted by 8 bits. So we'll have 56 bits here, and 8 bits will be free. In these 8 bits, we'll be fitting up ciphertext 2, and this will be going into an encryption strategy, and from there we'll get an output of 64 bits where we'll select the first 8 bits, discard the remaining 56 bits, and those 8 bits will be XORed with the plain text P3 of 8 bits. So we'll get the ciphertext 3, and this process will continue for PN input streams. I hope you're all clear with cipher feedback mode. The important advantage here is we can use the block cipher mode to actually as a stream cipher to encrypt streams of bits. So initially we have an initialization vector which is given to phase 1, and then we'll feed it to our encryption, and then we'll XOR the first S bits of that output to plain text P1. That is what is the meaning, to provide C1 which is of S bits. So again, this C1 is fed to the shift register after shifting the initialization vector in the shift register by S bits. Okay, this is just some theory of what we have learned right now. Let's look at decryption. How will you go with decryption? Again, it's similar. What we do is we take the initialization vector of 64 bits, some random number, and then we feed it to the encryption strategy. See, this initialization vector is the same as what we have used in the encryption. So we have to use the same initialization vector here. Both the parties should share that initialization vector, and that vector can be any number. But the same number should be used for both encryption and decryption. So we are passing this initialization vector to our encryption function, and it uses a key, as you can see. And what we get here is 64 bits output. So in this 64 bits of output, we are taking the first 8 bits. Say S is 8, we'll consider the first 8 bits, we'll discard the remaining 56 bits, and this output now is XORed. So we are doing an XOR with ciphertext C1. Say when you're talking about decryption, we are always working with ciphertext. So let's say we have streams of ciphertext here. C1 is 8 bits, C2 is 8 bits, and C3 is 8 bits, like that. So what we are doing here is we are taking the ciphertext, we are performing an XOR with this output. We'll be getting our plain text of S bits. Got it? So this ciphertext is also used for decrypting the next stream of 8 bits of plain text. So how it happens is, so we'll be shifting our initialization vector here. So if you have 64 bits of initialization vector, which we used in here, right, in round 1, what we are going to do is we're going to shift it by 8 bits. Since we assume S to be 8, we'll left shift it by 8 bits. So we'll have 56 bits remaining here. And then the remaining 8 bits, I'll just draw this here so that this is 56 and this is 8. So in this 8 bits, we are going to use C1, the ciphertext C1, which we have received. And we are going to feed it to an encryption strategy, use the key, and we are going to get 64 bits output. Now in the 64 bits, we select the first 8 bits, discard the remaining 56 bits, and those 8 bits from the encryption strategy will be performed. We'll do an XOR with ciphertext block 2. In decryption, we always work with ciphertext, right, to get the plain text. When you XOR it, you'll get plain text 2. So that's how decryption happens in cipher feedback mode. So what is the advantage of cipher feedback mode? We can use a block cipher as a stream cipher, and we can encrypt streams of bits, and it eliminates the need to pad messages to be an integral number of blocks. It can also operate in real time. So that is the advantage of cipher feedback mode. So if a character stream is transmitted, the characters can be encrypted and it can be immediately transferred. So we'll take a look at the next encryption strategy, the output feedback mode. The output feedback mode is very similar to what we have seen just now, the cipher feedback mode. So in the cipher feedback mode, we use an initialization vector, passed it to an encryption function. Then we took those 64 bits, the very first S bits we have taken. And what we did was we used those S bits and we did an XOR with plain text to get the ciphertext, right? And in cipher feedback mode, what we did was we used the cipher in the next shift register. Whereas in output feedback mode, we are not going to use the cipher. We are just going to take the S bits out of our encryption. We're just taking the S bits directly from here before the XOR step. We'll be using that in our shift register. So the S bits that we are going to use here is directly from our encryption algorithm, whereas in cipher feedback mode, that was from the ciphertext itself. So that is the main difference here. Otherwise, both cipher feedback mode and output feedback mode are used there to encrypt stream ciphers by using the strategy of block ciphers. So I have also given the difference here. Say in cipher feedback mode, let me erase all these things. Let's see the difference here clearly with these two diagrams side by side. Say in cipher feedback mode, we are taking the cipher text, which is an output of XOR of the encryption and the plain text, and we are feeding it to the shift register. So this C1 goes in as S bits here. Whereas when you talk about output feedback mode, we are not taking the ciphertext, we are taking the S bits from the encryption algorithm, that is the output of the encryption algorithm, and feeding it to the shift register. So these S bits are from the output of the encryption algorithm. So that's how the output feedback mode is different from the cipher feedback mode. So again, decryption is very similar to a cipher feedback mode. The only thing is in cipher feedback mode, we were using the ciphertext. We were using the ciphertext in the shift registers. Here, instead of the ciphertext, we'll be using the S bits, which is an output of the encryption mode. We'll be using those S bits in our shift registers to decrypt and get the output. It is very similar to cipher feedback mode, except for those S bits that we are using. Again, to repeat, in cipher feedback mode, these S bits were actually the ciphertext. Here, it is not the ciphertext, it's just the output from your encryption algorithm. So here we are taking S bits, right? Those S bits are used, and again, it is used for decryption. Uh, I think some of you might be confused. Let me explain this decryption. So we have this initialization vector of 64 bits, which is given, and this IV is also used in encryption. We are using the same IV in decryption. And what happens is this 64 bits, when fed to the encryption algorithm, it gives us a 64-bit output. So out of the 64 bits, we are going to take the first S bits, or we'll say 8 bits here, and we'll take the first 8 bits, and what we'll do is we are just feeding those 8 bits to our next decryption phase. So that is the difference here. So this 8 bits will be fed to the shift register, and we'll come to the next phase, but we'll take a look at this. So we are getting 8 bits from the encryption output. So we'll take this 8 bits, we'll do an XOR with ciphertext 1, which is also 8 bits, and this will give us an output of P1. This is 8 bits of plain text. So we have decrypted plain text 1 of 8 bits. And how the decryption of P2 happens is we'll take the 8 bits we received from the encryption strategy. We'll go here to the shift register. We'll use the initialization vector And what we'll do is we'll shift it by 8 bits. So initially the initialization vector is 64 bits. When you left shift it by 8 bits, we'll have 56 bits here. In the remaining 8 bits, what we'll do is we'll take this 8 bits from our output. We'll put those 8 bits here. And our initialization vector is ready of 64 bits. We'll feed it to the encryption strategy. We'll get 64 bits as the output. Now out of the 64 bits, take the first 8 bits, and what we do is we use those 8 bits. We'll do an XOR of those 8 bits with ciphertext 2 to get plaintext 2. So that's how decryption happens in output feedback mode. I might have been a little fast with decryption in output feedback mode because this is very similar to how it happens in cipher feedback mode. I hope you have understood all the block cipher modes that we have learned today. That is electronic codebook. The next one is cipher block chaining. The next one is counter mode. Then we looked at cipher feedback mode and output feedback mode and how these modes are different. That's all for today's session. Thank you.